My job is to take these great people we have and to push them and make them even better. The key to successful leadership today is influence, not authority. Outstanding leaders go out of their way to boost the self-esteem of their personnel. While looking at this factory, what are the outstanding leaders? This manufacturing plant consists of numerous production facilities made by different companies. Some of these intertwined machines are automated systems, but some are operated by workers. A problem may happen when the facility is working. We have to shut down the whole system until the problem is solved, which usually takes lots of time to find the reason for that problem. This is because there is no leader who can consider all the machines together and operate them as a whole. Therefore, now we're going to assign a leader who can solve the problem during an emergency. An excellent leader in a manufacturing plant is expected to aggregate data from all the devices and make correct diagnosis accordingly, so as to maximize the productivity of each device. That's the core technology of the manufacturing operation system as we thought. What is the AAS-based manufacturing operation system? We can see many applications in real life. You can easily access and utilize various functions through one operation system. The AAS-based manufacturing operation system has the same feature as it is operated by integrating all the production factors. And we call a factory that incorporates such systems Smart Factory. Why AAS-based manufacturing operation system is essential in future manufacturing systems? In 2011, Germany proposed Industry 4.0, which provided a new direction for its domestic industry development in line with the Fourth Industrial Revolution. The key vision towards 2030 is to achieve autonomy, interoperability, and sustainability. Future intelligent manufacturing factories can communicate with each other flexibly, for example, person to person to machine, and machine to machine, and it can achieve sustainable state through process autonomy and mutual compatibility. Through this, many tasks can be performed in a faster and more efficient way than now. The AAS-based manufacturing operation system is essential to enable process autonomy. In order to make machine and machine autonomously communicate with each other, the first key enabling technology is AAS-based digital twin. AAS-based digital twin technology is a digital representation of objects. Each object is given a digitized name such as ID. There is a cup of coffee. I'll make an AAS-based digital twin for an object of cup containing coffee. For example, the type, color, and size of the cup, the amount and temperature of coffee in the cup, etc. Each of these characteristics is digitized and named individually. Now, we can describe all the characteristics of a real cup in the digital world using the AAS-based digital twin we made. But what if three people, Chosu who lives in Korea, Michael who lives in Germany, and Anna who lives in the United States, make their own AAS-based digital twins for the same object? Three people make AAS-based digital twins for the same object, but they cannot understand and utilize each other because expression ways are different. Thus, the AAS technology can help freely express and exchange all the characteristics and functions of a same object using a standardized language the machines can understand. Let's enter a real factory. There are many devices connected with each other in this factory. If these devices are represented through AAS-based digital twins, then devices will be able to autonomously communicate with each other and flexibly execute tasks in digital world, like the communication among humans. In addition, this is not just the communication among devices, but it can also be extended to the communication between factories. Data generated at the manufacturing site use different rules depending on the manufacturer, such that their expression forms are all different. Edge connectivity helps connect various manufacturing sites. It connects different network technologies, converts field data from different systems into structured data as defined by AAS. AAS-based manufacturing operation system plays an important role in analyzing the production process by collecting data from all the production equipment in real time and assigning meta-information to those collected data. In particular, some data which were collected without a specific purpose can be important from the perspective of other devices. Through this data collection and analysis process, various measures can be proposed to improve productivity and reduce defect rates and costs. A typical application example of AAS-based manufacturing operation system is Abnormal Signal Detection Service. By continuously accumulating the data, we can detect and prevent failures in advance, which are usually hard to be predicted during the design process. Even if a failure occurs during the operation, the failure reason can be quickly identified based on the device configuration information and operation state information. Finally, the device can be repaired in a fast way. If a device needs to be replaced, we can utilize its digital information to quickly find the same model or replaceable model. In addition, the plug and produce scenario can be used to minimize the setup time when replacing a new device, and can also quickly acquire device information in case of failure, so as to dramatically shorten the production interruption time. In this way, we can prevent failure in advance or respond quickly to the failure once it occurs, which will greatly increase the workplace safety and improve the productivity. When new products need to be manufactured, devices firstly interact with each other to analyze and compare the manufacturing information as well as their own device information. Afterwards, qualified devices are automatically selected and ready to manufacture new products. An optimal production process is automatically proposed. Then the operator will select the most appropriate option, and accordingly the production process will be autonomously adjusted, and finally the production starts. The significances of the AAS-based manufacturing operation system are not limited to production and operation. It also plays an important role in reconfiguring new factories or production lines. From the design stage, the most suitable devices are firstly recommended in the digital world, and then we can do simulation using that digital information before ordering real devices. One factory is organically related with other factories to supply components and devices to it. Considering this, the role of the AAS-based manufacturing operation system is quite important. And appropriate information and feedback are shared along the entire value chain, for example, beyond one factory itself, and among different businesses. It will help create more effective business relationships. We chose a real production line as the demonstration manufacturing line and applied AAS-based manufacturing operation system. Through the edge connectivity provided by the AAS-based manufacturing operation system, all the data generated from the production process can be collected through the middleware and linked to some representative smart factory services, for example, production management system. The manufacturing process consists of various devices and unit processes, and each process and device are composed of various solutions using independent network technologies. The edge connectivity layer of the AAS-based manufacturing operation system utilizes various data conversion solutions to collect data generated from different solutions and then structure the collected data based on the AAS information model so as to enable consistent data management. The middleware manages the AAS-based manufacturing operation system and provides real-time collected data and historical data to the service module through a uniform interface. It provides simple dashboard functions for visualizing real-time collected data, historical data, and AAS management functions. In order to realize a more advanced AAS-based manufacturing operating system middleware, we have built an abnormal signal detection artificial intelligence platform to detect abnormal signal patterns from the real-time collected data through machine learning. The AAS-based manufacturing operation system can provide various smart factory functions by utilizing the data collected from the manufacturing site. In the edge connectivity layer, we additionally provided a protocol conversion device to collect data from PLCs, which were already built on the demonstration manufacturing line, and then converted the PLC data using legacy field bus technology into OPC UA data. We analyzed the demonstration manufacturing process and divided it into several specific processes, analyzed devices and data for each process, and finally, modeled the demonstration process into systematical AASs. The created AAS not only includes real-time operation data for the target process, but also includes the device identification data and technical specification data, etc. In addition, the metadata with explicit meaning, type, and unit is also modeled into the AAS. AAS-based data is collected through the edge connectivity of middleware. Middleware is built with a message bus structure so that multiple service modules can quickly share the data collected in real time. The collected data is shared through the messaging bus, stored and utilized in the time series database module, and then selectively transmitted to the 3D digital twin model to demonstrate the real-time state of the process on the screen. In the artificial intelligence platform, abnormal patterns are detected in real time based on the information learned from the selected data, and the process data can be freely used by upper services such as MES. The historical data stored in the time series database can be used for artificial intelligence learning, performance analysis, failure response, and strategy optimization in various upper services. 2D Dashboard is a default package provided by the middleware to visualize the main data among all the collected data that needs constant monitoring. We selected the main information of the demonstration manufacturing line and accordingly designed the image on the screen. The Resource Monitoring Dashboard allows you to monitor the current status of major resources such as computing power, memory, and storage capacity required to operate the AAS-based manufacturing operation system. It is possible to design the most appropriate driving environment for building the AAS-based manufacturing operation system. Through the package browser, you can manage the AAS model that is used in the manufacturing operation system, and all the configuration settings for performing data collection can be automatically executed through AAS's internal conversion function. We implemented a 3D dashboard service which can show the operation status of the demonstration manufacturing line as a 3D model. The 3D dashboard service shows the appearance of the entire factory and key indicators for various processes inside of the factory, and also illustrates the operation status of the demonstration manufacturing line in detail. Middleware can collect data from actual manufacturing sites within 100 milliseconds in average, and can also deal with more than 3,000 transactions per minute. As such, the 3D digital twins can display the actual factory state in almost real time. The 3D dashboard service receives and then displays major performance indicators from the production management system service. Middleware plays a key role in data exchanges between these services. Services such as 2D dashboard and 3D visualization are representative real-time data services that can help you intuitively and quickly check the state of the process. Conversely, abnormal signal detection service is a representative service which utilizes historical data that has already been stored. We further generalized the service such that it can be widely used in smart factories as an abnormal signal detection platform, and it is connected to the AAS-based manufacturing operation system. Abnormal signal detection platform is an AAS-based service that can learn normal signal patterns through selected datasets and analyze the collected data in real time to detect abnormal situations in advance and make preventive responses. Currently, it has been confirmed that abnormal signals can be detected using test datasets, and we are also trying to verify the learning functions using the datasets collected from the real manufacturing process. So far, all the functions of the manufacturing operation system that we have seen are implemented through a digitalization technology called AAS. Moreover, data collection process is also automated via AAS. In order to automate the data collection process using AAS, a conversion function that can extract AAS information models from various forms is required. An AAS parser is a core function for performing such tasks. The package browser equipped by the middleware provides a conversion function via the AAS parser. Through the conversion function, AAS can be converted into a network configuration file, an information model file, and an engineering file, which will be utilized by middleware and edge connectivity. In order to apply the AAS format to a system which is incompatible with it, it's necessary to convert the AAS to the format supported by the system. Therefore, we developed a rule-based automatic switching system that can convert AAS configured with XML schema into JSON, or convert AAS configured with JSON into XML schema. This conversion technology is expandable because AAS-based technology can be applied to various industrial fields in practice. We have developed a MOM platform oriented for AAS-based manufacturing operation system. Herein, convergence and communication infra layers are operated by MOS that transmits data to microservice architecture-based services through messaging buses. Such a cloud-based infrastructure guarantees the scalability and stability, and the resources needed for remanufacturing can be minimized through applying or reusing microservice architecture-based services. In order to efficiently utilize the features of the cloud, we have established a development environment for constructing native cloud architectures. Based on the microservice architecture, it is able to guarantee the flexibilities supported by microservice, such as generalization, production, restraint, quality, facility, and reports, and also guarantee the service stability by preventing failures. The systems defined in Mesa ISA 95 and Siemens MindSphere type were taken into consideration when constructing specialized service manual for assembling automobile parts. To provide logistics automation services in the factory, AMR and AMR control systems were designed and developed. By connecting with the system through 5G wireless technology, AMR has developed a web-based solution that can identify the location of AMR and monitor its status in real time. Accordingly, existing factory logistics can be flexibly adjusted based on the real-time requirement. Before implementing AMR, we developed a function that can perform pre-verification through simulation, for example, based on Automation ML-enabled digital twin. In accordance, it is possible to detect problems in advance and respond to various potential problems before field application. In addition, even if there are only 1 or 2 real devices in operation, we can verify the expanded case using simulation when 10 to 20 units are added. We verify the plug-and-produce scenario by applying AAS-based manufacturing operation system, edge connectivity, and middleware solutions to the test bed. In addition, in order to minimize the workload required for AAS development, an AAS reference model for common equipment such as robots, AMR, and CNC was developed and applied to the test bed. We will build, disclose, and distribute open-source websites for mid-sized and small-sized enterprises to easily access digital twin solutions, which are developed and verified through this project. Solutions will be verified through ICT Convergence, AAS-based manufacturing operations system development and demonstration projects, and the reliability will also be guaranteed through the Industrial Internet Consortium certification procedures. In addition, through expanding projects not only for central but also for mid-sized companies, more than 150 practical cases will be created around the Gyeongnam region. AAS-based manufacturing operations system aims to improve the productivity of manufacturing companies by building smart factories with the objectives of acquiring manufacturing data easily and quickly. In the first stage, we proposed a solution that can systematically collect and utilize field data. Moreover, the feasibility and performance were confirmed by applying the solution to a demonstration manufacturing line. In particular, we put the focus on the visualization of data collection and verification. In addition, we have established a suite of strategies to quickly disseminate and deploy these related technologies in small and medium-sized manufacturing companies in Korea. Based on these achievements, in the second stage, we will develop technologies with the goal of establishing edge connectivity that can be applicable to various manufacturing environments, developing middleware that can provide more systematic data interfaces, various data services oriented for use case testing. In face of the fourth industrial revolution, we are heading for a greater future. This is because there is an advanced manufacturing operation system made through the efforts of representative cutting-edge companies. In the future, the established manufacturing operations system is expected to help Korea grow into a global leader in the era of Industry 4.0.